In this section, we learn about object detection and recognition using image feature and descriptor matching. These powerful algorithms can identify known objects under varying conditions and have proved extremely useful in many diverse fields such as robot vision and localization, image alignment, and product identification apps. Many applications require the ability to identify and match previously seen images. In video stabilization, these can be previous frames that need to be non-rigidly matched despite camera motion, but they can also be images of objects like products that need to be identified when stumbled upon. Street mapping and robot localization apps need ways to match and align street photos for visualization and self-localization. A good object detection or redetection system must be robust to a variety of real-world challenges. For example, it must be able to identify the object under different lighting and illumination conditions, in photos taken by different cameras at different times and from different angles and positions relative to the object. It should also be able to robustly identify the object when it appears at different scales and resolutions. Video stabilization and image stitching are applications that require accurate image alignment. Our image detector must be accurate enough to allow such alignment while still being robust to missing image information such as clipping or occlusion. To top it all off, we'd like our system to be as fast as possible to allow real-time operation even on mobile devices. This is quite a shopping list of requirements and challenges. In this section, we learn about a family of algorithms that try to tackle these challenges. We'll use image features to quickly find interesting points in a photo. Feature descriptors give us robust and compact alternatives to pixel intensities for representing the structure and texture around each feature point. Descriptor matching algorithms let us match the descriptors found independently in two photos. Having matched two photos, we can now robustly align them using the matched feature points. Let's take a closer look at image features. When we try to recognize an object or identify a photo, it is clear that some parts of the photo are more distinctive than others. Image features are prominent areas in the photo that are most likely to remain distinctive regardless of the conditions under which the photo was taken. Furthermore, we would ideally like them to be detectable regardless of the apparent size and resolution of the object in the image, but still be consistently scaled relative to the object itself. Classic image features include image corners or image edges. Although these features are invariant to the object resolution in the image, they generally do not provide enough relative scale information. In the late 1990s, a new class of image features began to emerge. These were progressively faster, often faster than the simple classic edge and corner detectors, while also providing both relative scale and even orientation. Another important design consideration was repeatability. The same set of features would tend to be detected in two photos of the same object, even under significantly different capture conditions. It is important to note that feature extraction operates on a single image. It does not depend on any other photos. In the example, we can see the extracted features, also known as key points. Note that no key points were detected in the blurry background, since they tend to prefer high contrast, sharp, and distinctive regions. Each key point is marked by a circle whose size indicates the feature scale relative to the image, and the radial dial inside the circle indicates the assigned orientation of each key point feature. OpenCV implements many feature and descriptor algorithms. Let's see how easy it is. Before matching descriptors between images, let's see how simple it is to detect image features. We will load our images in pairs. We create our feature detector. In this example, I chose the Akaza detector, though other detectors work similarly. We declare two key point vectors to hold the detected feature points using the CV key point type. We call the detect method to detect features in image 1. The detected key points will be stored in key point 1. Remember that feature detection is done independently for each image. So here we detect the features in image 2 and store the detected key points in vector key points 2. That's really all there is to it. All that's left to do is display the detected key points. The OpenCV draw key points function conveniently makes this trivial to do. We call it and show the key point image. Similarly, we call draw key points for the second image. In this case, we also pass the draw rich key points flag, which will also draw an indication of the orientation and scale of each feature. Now let's run it and see the results. Nice! We can see the first image with the key points marked with randomly assigned colored circles. Here is our second image. Note that it has a different size and that the cookie box appears at a different orientation and is even partially occluded. We can see the detected features, but in this case, each feature point is indicated with a circle whose size indicates the feature scale and the internal dial indicating the feature orientation. Remember that since each image was analyzed independently, there is no relation between the randomly assigned key point colors in each of the images. Let's see another example. Here is the first photo with the detected key points, and here is the second close-up photo with its own set of detected feature points. Note that many of the points in the first photo are completely outside the second photo field of view, and conversely, the close-up photo contains many more detected features on the round window than the first. We shall soon see that despite this disparity, we can still achieve a good match between these two photos.